everyone, TA Leo coming at you live here. I want to start off first by apologizing for not being able to make this video earlier to you guys. I really apologize for that. I've had a power outage that lasted about 3 days, and as many of you probably know, once you fall behind one day for classes, it feels like you fall behind for 3 days. As many of you probably know, with the amount of work that we receive on any given week for the semester. But I digress. I'm glad that I'm able to do this anyways for you guys. So today we'll be talking about FTIR and GCMS, and in particular, how to prepare samples for instrumentation. So here's a picture that I found of an FTIR instrument, and here's a picture of the GCMS instrument that is used. Now, in terms of preparation for FTIR, the sample doesn't actually have to be prepared further. So what we're going to talk about here in a second is, rather than the preparation of the sample, we're going to talk about how IR actually works. And I'm going to do that using a piece here of the notes that I've taken from when I took organic chemistry back in the fall of, what was it, 2018, I think? Yeah, 2018. So, with that being said, we will talk about how the sample is prepared further for GCMS. So when it comes to GCMS sample preparation, you have to have two things in particular. A particular kind of vial that is used for GCMS that has a septa with it. And what's important about the septa is that it allows us to be sure that no contamination occurs and that the needle from the instrument can puncture the vial. So in other words, the septa is used by the machine here, sorry, the instrument here, to be able to puncture through and acquire the sample, and it's also a mechanism to avoid any contamination by the needle itself and as you're moving around and using this vial in the lab. We also need a pipette with a Kimwipe packed into it in order to be used as a filtering mechanism. And this is important so that we avoid any solid particulates to get into the sample, such as sand, that can jam or clog the GCMS column, which is no good. So this filtering mechanism is important to make sure that there's no potential particulates such as sand or anything else that can get into the sample and thus jam the GCMS column. So in terms of actually doing this and actually preparing the sample, you're going to need two pipettes in particular. So pipette number 2 here is labeled number 2 here is the pipette with the Kimwipe for filtering. And what you do here is you place the pipette into the filter pipette into the vial as shown here, and then you use what's labeled here as pipette number 1 to actually acquire your sample. Now, when it comes to acquiring a solid sample, you just need a very minute amount of the sample. You don't need that much, literally just a little piece of it to get GCMS to work. In terms of a liquid sample, all you have to do is use the power of capillary action to be able to acquire the amount of liquid needed. So as you can tell here, based on that, there's not that much of the sample that is needed for GCMS. It's a very sensitive instrument, and so because of that, you don't need much amount of the solid or liquid sample that you're using. So the setup is the same as shown here. You have the filtering mechanism at the bottom with labeled as pipette number 2, and then in pipette number 1, that's where you actually acquire your sample. And what you do here after setting up this kind of apparatus is you take hexane, which is our solvent for this experiment, and then put some hexane in there to push the solid or liquid down, and then filter it using pipette number 2, which then leads whatever is filtered out into the actual labeled file itself. Now, what's important here to note also is that whatever it is that you're filling the vial with, that it doesn't pass the shoulder of the vial, which is shown here labeled here as the shoulder. So it shouldn't pass the shoulder. You don't want to overdo it, but you also don't want to be below about 1.0 here as well. So this is the setup for GCMS. Just to reiterate, you take one pipette that is packed with Kim-Whites for filtering, and then you take another pipette to actually acquire your sample, which then you add hexane to then filter out that sample and then get your prepared sample in the vial shown below. Now, when it comes to FTIR, like I said earlier, the sample doesn't have to be prepared further. You can just take the sample itself straight to the instrument and start using it. So instead, what we're going to talk about here a little bit is just how IR actually works. Again, like I said earlier, this is a little piece of the notes that I took from when I took organic chemistry, and we're just going to use it to just kind of talk about how IR actually works. So, IR has a light source that emits light and hits the sample as shown here. Now that light could also be referenced to as heat energy. So what happens here is the heat energy, or in the form of light, hits the sample, and the sample absorbs particular wavelengths to then transmit another wavelength that is unique to the bonds that are in that sample. So using the notes here, the bonds use the heat energy to stretch, vibrate, and bend. You can think about that as a dance. And then the energy that's not used to dance will be transmitted. And only certain types of bonds are danceable per se. So in other words, only certain types of bonds will emit certain types of wavelengths of light to the detector here. And then thus, using that detector and using those particular wavelengths, you can start to infer what kind of bonds are in the structure of the sample that you're analyzing. And so IR helps answer really one key question. And that question is, what kind of bond is present, or what kind of bonds aren't present in that sample, as you see there. So just to reiterate, there's a light source that comes from the IR instrument that hits the sample. The sample absorbs particular wavelengths, and as it absorbs particular wavelengths, it then transmits particular wavelengths to the detector, and then with those wavelengths, we can start to postulate what kind of bonds are in that sample, hydroxyl groups, carbonyl groups, etc.